Thank you. My name is Ayenew, and I will be presenting our paper, which is on adaptive hazard zone model for improved safety in highway work zones. When I come to the introduction, worker equipment interactions are one of the major factors contributing to accidents in highway work zones. And a common way of mitigating such risks is by drawing a hazard zone around the equipment. Such hazard zones are traditionally static and does not consider the different factors such as equipment speed. Due to this, they have several limitations which can be summarized with these points. As I said, the first limitation is the fixed size won't adjust based on the equipment kinematic data such as speed or acceleration. And due to this, there would be high false positives at low speeds, which means unnecessary alerts which may disrupt work and could have high um, false negatives at high speeds, which will lead to increased accident risks. So the other thing is in highway work zones, which is a relatively dynamic environment, static models will fail to provide accurate hazard assessment. So the objective of this paper is to propose a hazard zone model which dynamically adjusts hazard boundaries in real time based on equipment movement. And the proposed adaptive hazard zone model will dynamically adjust hazard zone size and shape based on, as I said, real-time equipment data. It uses probabilistic approach with bivariate Gaussian distribution, which will result in different hazard zones or different boundaries for different risk levels. And then it also provides a more realistic representation of hazardous areas, like, for example, rather than being a circular hazard zone, it will be like elliptical with an elongated um, um, size towards the direction of movement. And the other thing is it will ultimately reduce false alarms and misdetections when we compare it to the common static model. When I come to the meteorology part, we basically have done two things. First, we have derived the mathematical model for the hazard zone, and then we have tested it in software simulation environment. So for the mathematical model, as I said, we used a 2D Gaussian distribution. So we represented the standard deviations in x and y directions based on the equipment data, including speed and acceleration or deceleration. In addition to the movement data, we have also used the equipment footprint, like the length and width of the equipment, the initial boundary, safety boundary, which is the safety boundary which is required for a typical stationary equipment, and the operator reaction time and equipment stopping distance, which are related to the speed and the acceleration of the equipment. And finally, we came up with a formula for the minor and the major axis of the hazard zone, which is actually a 2D projection of the Gaussian distribution. So we have like different distribution projections for different risk levels. So this is a typical projection. The next step was doing simulation. So we chose Weibo software for the simulation because it has the features that we need for our target. So we tried to come up with a realistic road environment there, and we used the sensor features to track the speed and acceleration of the equipment. In addition to our proposed hazard zone, we have also done simulation for a typical static hazard zone, circular hazard zone, so that we can compare the results of both. So we have done 100 test cases for both for each of the hazard zones. And finally, we have got these results. We try to compare the results based on accuracy and other factors. When we come to the accuracy, as you may see here, the adaptive hazard zone model has 93% accuracy, whereas the static model has 60% accuracy. And when we see the confusion matrix, the true positives, true negatives, false positives, and false negatives for both cases, for both hazard zones could be seen here. We have also tried to compare the results based on speed range, different speed ranges, starting from low speed to high speed. So it can be seen that for all cases, the proposed hazard zone is better than the static hazard zone, and especially for medium and high speed ranges, the difference is significant. And in addition, it can be seen that the static hazard zone has significantly higher false positives and false negatives, especially for the medium and high speed ranges. And here are our conclusions. The adaptive model, which is the proposed model, has higher accuracy. It has lower false positives, which is 3% versus the 24% for the static circular hazard zone. It has also lower false negatives, which is 4%, compared with 60% of the static hazard zone. So we can say that the proposed model has the potential to be alternative to the static hazard zone for a more accurate and efficient hazard detection. The main limitation of this research is the validation is only done on software simulation. So in real world scenarios, factors such as sensor noise and drift may affect the accuracy. So as a recommendation, field experiments to validate in real world conditions is better for final application of the hazard zone. The other thing is we have used a static worker position, so dynamic worker movement, which is the real scenario in highway work zones need to be considered for a more effective and practical application. And finally, the research is supported by Minnesota Department of Transportation. And here are the contacts of the authors. Thank you very much.